Hello everyone. Today we are going to discuss about recurrence relations. So recurrence is basically a function. In our previous lectures when we talked about functions, we have mostly seen closed form functions. That is, we could derive upon an expression of a function completely. However, in some of the parts of our lecture we have also seen when we compute the number of onto functions possible is that some functions are such that they could be defined within a restricted environment by calling itself. More, you have used these examples when in your programming course you use the concept of recursion, which says that you can declare a function by calling itself with lesser number of instances. In today's lecture, we will see what is the mathematical foundations of such kind of concepts, and we will see that how these kind of recurrence relations are day-to-day used in solving computer science problems and analyzing different recurrent problems. So to begin with, as I just suggested, that recurrence relations are mathematical equations with respect to functions. That a recurrence relation is an equation which is defined in terms of itself. So to give you some example, our natural computable functions can also be expressed in recurrence, because when we say something to be computable, then we have some iterations or some kind of fixed set of operations going over that function, deployed over that function to compute the final result. So as you can see that we could have linear functions which we could describe as f of n equal to f of n minus 1 plus 1, which means that this function is dependent upon the previous value of this function, which is with n minus 1 number as input, and I add the answer with 1 to get this function. So as you can see that this goes down till we reach certain base condition. So either it is f1 or it is f0, we have to define that base condition, because unless we will iteratively try, if we try to compute what does fn do, then we have to iteratively try to compute what does fn minus 1 do, and then we will compute what does fn minus 2 do. So somewhere we need to stop and get the value which is f1. So if you expand this function, this will be fn minus 2 plus 1 plus 1, then it will be fn minus 3 plus 3, and so on. So you will get finally the closed form is fn equal to n. We have also seen quadratic or polynomial type of functions where you can say fn equal to fn minus 1 plus n. So definitely when you try to expand this will be fn minus 2 plus n minus 1 plus n. Again you expand, it will be fn minus 3 plus n minus 2 plus n minus 1 plus n. So you can see if you go till n equal to 1, you will get the summation of 1 plus 2 plus 3 up to n. So which is basically n into n plus 1 by 2, and this formula results. We can also define functions like fn equal to 2 into fn minus 1, which means that your fn minus 1 will again be 2 into fn minus 2. So fn will be 2 square into fn minus 2. And if we go till 0th point, so it will give me 2 to the power n as the answer. Similarly, this kind of weird function we have expressed, and we already know that this is n into f of n minus 1. If we expand it, it will go as n into n minus 1 into n minus 2 up to 1 or 0, and which is termed as factorial n. So what is common in all these four functions is the fact that every function can be defined with respect to itself, and it's an equation. Upon expanding or upon solving those equations, we get certain closed form. So therefore, since our computation is a recurrent options many a times, so we need to study such kind of functions and need to study the behavior, or how can we solve such kind of a function to finally get an expression. You may rightly be thinking that this is kind of related to mathematical induction, where we also describe the recurrence in terms of it's a function which is of lesser number of arguments or less value in the arguments, and we have a base condition check. So suppose we have this kind of a recurrent function with a base condition t0 equal to 0. So mathematical induction tries to prove whether this is true for the base condition, and assuming this is true for n-1, it tries to prove a closed form expression for that. So let us say the closed form expression we guess here for this recurrence, that is the value of Tn finally will be 2 to the power n-1, and we check in the base condition whether 2 to the power n-1 satisfies. It satisfies because base says it is equal to 0. So our induction hypothesis, that's why for the n-1 instances will be 2 to the power n-1 minus 1. So if we substitute here to find the Tn value, it will coming as 2 to the power n-1. So we can prove through mathematical induction the same thing. Since this recurrent nature is with a base case is just mimicking the mathematical induction. So many times when we try to prove whether we reached to the final solution which is correct or not, we could start with the final solution and could invoke the rules of mathematical induction to prove it. Finally, we will see that these are very basic or naive examples of recurrences. However, there are many categories and classifications of recurrences, such as which is called first order, second order, or kth order, higher order. We have linear recurrence versus non-linear recurrence. We have homogeneous versus non-homogeneous, and even we have constants and variables as coefficients in the function when declaring the recurrence relations. So in this lecture, primarily we will try to see that how we can define in generic sense such kind of a recurrence relation, and what are our mechanisms to formally solve these recurrence relations and build a closed form expression for it. And as you can see, numerous applications in computer science domain for these recurrences. Mainly it is applied to algorithm analysis of time complexity and all, which we will eventually use this recurrence to solve those. Many times it is also used for counting, problem solving, and since in reasoning as well, since a huge instance of the problem can be broken down, as in case of recursive problem solving or in recurrence relations, you can see that a huge instance can be broken down into smaller instance and can be reasoned out to find out certain phenomenon. So we use this kinds of mathematical techniques over recurrence relations to in diverse application domain such as these. So the whole set of lectures over these recurrence relations will try to formalize such recurrence relations and try to devise mechanisms in which in a way such that we could solve it very elegantly. So to begin with that, what we are going to solve and how do we formulate such recurrence, let us try to start with some problems in our hand. So first problem says that what is the maximum number of regions possible in a 2D plane with n lines? So how do we try to address this kind of problem? So when we say maximum number of regions possible in 2D plane, so we start with certain kind of observations with. By the way, this problem is proposed and solved by Jacob Steiner in 1826, and we will see gradually in this lecture that such recurrent problems started defined in long back in 18th century or earlier, and then gradually we will see there are still standing some recurrence problem which people solved in 1-2 years back also. So this is a journey where we see that which are the ways we can formulate a problem to be a recurrence problem, and how do we formulate that, how do we solve that. So some kind of problem examples we took. The first one is this. So when we say maximum number of regions by n lines, there are certain observations we could find out in this problem statement. That no line is parallel or collinear with each other because we are trying to see maximum number of regions. So if 3 lines are collinear, then the number of regions will be lesser than all 3 lines intersect at different points. Parallel obviously it will just produce n+1 number of different regions. So we can do better than that. So when we say maximum number of regions, obviously we are not restricting into parallel and collinear lines. The second observation is that, let's say I have n lines in the plane. You may simultaneously draw as I discuss. So you have n lines which are non-collinear. Let's say you have 3 lines in the plane which are non-collinear intersecting at 3 different points in that plane. Now when you try to introduce the 4th line or the n+1th line, it will intersect with every line exactly once. What does it convey about the number of regions that is going to be formed? See, we are trying to define the problem in terms of recurrence. So, we assume that we have a set of regions already present with n line intersecting and present in the plane. What happens with the n plus 1th line? So, if that observation we could somehow frame, then we will say my number of lines for n plus 1, a number of regions for n plus 1 lines is equal to the number of regions for n lines plus the observations that I will get for n plus 1th line introduction. So, first observation was that it intersects with every line exactly once. The second observation, which is most crucial, is start from one end of this n plus 1th line and proceed to another end. You will see that every time it just intersects a line, just before that, it bifurcates or divides the previous region into two. That means, when n plus 1th line goes to intersect with any of the line, just before that, the region which was there is increased by one in number, because it just divides that region while intersect and pass through. And finally, when it has the last intersection and goes out, then that infinite region after the last intersection also gets divided into two parts. So, what does this observation 2 and 3 summarizes? Or rather 1, 2 and 3 summarizes is that every n plus 1th line intersects with every other n lines exactly once, and while it is intersecting, it increments every region by once. So, n number of regions get incremented, plus the last one, when it tries to go out, the last region also gets increased. So, therefore, I have n plus 1 region increased when I introduce n plus 1th line, which is crucial to form the recurrence, because we say that we have already n lines and then we are introducing n plus 1th line. So, in general, we will say that the recurrence, which says that the number of regions formed by L lines is Ln, then that is equal to the number of regions formed by n minus 1 lines already there, plus the introduction of the nth line, which cuts through all n minus 1 line and creates a new region, plus when it goes out after the last line cutting, it increases one more region. So, that is total n region it introduces. And we know that if there are no lines, so your whole 2D plane is a single region. So, therefore, the base condition is 1. So, this is how we formulate the recurrence. Now, as you can see that one of the way to solve it is just by expanding it, because this is a very simple recurrence. So, we can expand Ln minus 1 again as Ln minus 2 plus n minus 1. Then Ln minus 2 as again Ln minus 3 plus n minus 2. So, the whole thing gets extended like this. And now you can see a pattern, which that pattern goes till n minus n. That means it will be L0 plus 1 plus 2 up to n, which is L0 is 1. So, 1 plus it is the summation of the natural numbers from 1 to n, which is n into n plus 1 by 2 plus that 1 for L0. So, this is the closed form formula for the number of regions in a plane when n lines which are not parallel and not collinear passes through in a 2D plane. So, see how we formulated based on the problem definition the recurrence relation, and how do we naively solve it. So, let us complicate this example a little bit more. So, regions using bent lines. That means instead of giving you straight lines, I will give you V-shaped bent lines. So, it will have one bend only, the straight line will have one bend somewhere. So, it is just like looking like V-shaped or wedge-shaped, this V-shaped. So, now if I ask the same question, how many maximum number of regions are possible? So, as in earlier we have that observation. So, see, this is just a variant of the straight line problem. So, let us observe that what happens here. So, no V-shaped bent line tip will coincide with the tip of another bent line. The same as since we are trying to declare maximum number of regions. So, if the two tips of the V-shape falls in the same point, then the number of region would be 4, whereas if you cross that bent line in a different manner, then the number of region increases. So therefore, since we are considerate here about the maximum number of regions, so I do not want two tips to be at the same place. Second observation. A bent line is just like two straight lines, except at the point of merging, and beyond that I do not extend those lines, isn't it? Because you have two straight lines. Consider the symbol V. You have two straight lines and you have a tip where you intersect. So earlier in our case, we just extended those two straight lines. Here, after the tip, we do not extend it. So therefore, reaching to the tip, these two straight lines will exactly take the same number of regions that is being done with the earlier case. Beyond the tip, now the question is, so observation 1 suggests that it is just like adding. So if you have one V-shaped bent line present in the plane, so your nth bent line is just like adding 2n number of lines and the regions in the plane. Except the fact that do we lose something because we have stopped here after the tip extending the straight line. So the tip point must lie beyond the intersection with the other lines. That is all we lose. So see, if we have two straight lines which is extended beyond the tip point, then we form the regions 2, 3 and 4 with that. Because one is inside the V and the other 3 where if you extend that V after the crossing also, you have 3 regions. Now what you do is that you merge those 3 regions and make it 1. So that means we lose only 2 regions per such kind of a V-shape per line. So we lose 2 regions per line, and now introduction of a V-shape introduces 2n number of lines. So if you compute the same thing with 2n number of lines per V-shape minus that you lose 2 into n number of regions, that will give you the final recurrence. Now, to understand and justify more, just draw 2 V-shape and try to figure out whether this happens or not, instead of drawing 4 intersecting lines and stopping it on the tip. So the maximum number of regions formed by n bent line is just introducing 2n lines and all possible regions that I can get, minus, since we are not extending those 2 lines after the intersection point, so every line potentially loses 2 regions per line. So that is minus 2n number of lines we need to reduce. And again, if we have no V-shape, then the whole region, the 2D plane is a region. So that is number 1. So we can solve it because we know the closed form of this, because this closed form is n into n plus 1 by 2. This is 2n into 2n plus 1 by 2 plus 1 minus 2n. So it gets 2n square minus n plus 1. So see, the lesson to be taken here is the fact that it may not be always the case that you need to devise the recurrence relations in terms of itself, but a recurrence relation can also be with some other recurrence as well. So it could also take help some other function which is a recurrence function. So that then also this relation is a recurrence relation. Let us come to a very famous problem that you have already know as part of your programming and data structure course, which is called the Tower of Hana. So to give you a complete description, it's just you have to transfer n disks with 3 pegs, and your job is to transfer those n disks from source peg to a destination peg. That is, we will say source peg as A, destination peg as B, using the third peg auxiliary as C, and you cannot place a bigger size disk above a smaller size disk. So always smaller size disk is placed above the larger size disk. And at start you have n disk positioned at peg A, that is your source, and it is stacked in their descending order of size bottom up. So it is stacked in a well sorted bottom up in their order of size. So the lowest element is the largest and the topmost element there is the smallest. And in any point of time during this transfer, you are not allowed to place a particular disk which is of larger size above or on top of smaller size disk. So now the question is that can we formulate the number of steps or movements for this? So the recursive solution to this problem was first proposed by Frankos Edward Anatoly Lucas in 1883. So it says that if we have one disk, it's very easy because we just move from peg A to peg B, and this is our base format of our recurrent thinking. The second is that if we have more than one disk. So you can think it the more than one disk means that I need to place the larger disk from peg A to always peg B. So to free the larger disk so that I can move, I need to move all its top n minus disk to the auxiliary one. Then place the largest disk directly to the destination, that is peg B. And then the n minus 1 disk that was there in the auxiliary one, I take help of the auxiliary peg as A and place this on my final destination point B. So see, the recursive formulation of this problem says that you solve the problem with n disk using n minus 1 disks going from peg A to peg C as auxiliary B. Therefore, your solution to the problem is A is the source, C is the destination, and B is the auxiliary for this n minus 1 disk. Then the largest disk is free to be placed from directly peg A to peg B. And then I have n minus 1 disk again from peg C as a source, peg B as a destination, using peg A as auxiliary. So the red thing are my recursive formulations to the problem using smaller number of instances, that is the less number of disks. And the blue one here are the direct moves. So blue one actually contributes to the number of moves and the red one contributes to the call to the same function. So therefore, we could, looking by this strategy of solving, we could easily see that if Tn be the number of movement to transfer, then it first transfers n minus 1 disk. Then it places, so this the number of movements done by n minus 1 disk plus the larger disk into the middle or the destination peg, plus putting back all those n minus disks which were waiting in the auxiliary towards the destination. So therefore this is Tn minus 1 for n minus 1 disk movement, first red one, plus 1 this one, and this is the last red one. 1 for n equal to 1, as you can see, I just have to directly move it. This is my base condition. So if you simplify it, it is Tn equal to 2Tn minus 1 plus 1 for n greater than 1, and my base condition is T1 equal to 1. Can you remember that we have solved this in our introduction slide just by expanding it, or just by using mathematical induction over it, guessing the solution? Now we can also do it by expanding. So we can say that Tn equal to 2Tn minus 1 plus 1 equal to, this is again 2Tn minus 2 plus 1, which will be 2 square Tn minus 2 plus 2 is outside, so plus 2 plus 1. So therefore, if you expand, it will be 2 cube Tn minus 2 plus a GP series of 2. And finally, if you go till T1, it will be 2 to the power n minus 1 T1, and this is just a GP series up to 2 to the power n minus 2. So T1 is 1. So it's a GP series of till n minus 1, and if you solve it, you will get 2 to the power n minus 1 number of transfers required. So this problem you all know. Now let us just try to have little bit variant of this problem. Instead of giving you 3 pegs, if I would have given you 4 pegs, is your solution going to improve, or your recurrent thinking of solving the problem going to improve or not? So now you try to see that, well, you have an auxiliary peg here which helps you to move certain kinds of disks in between and then place the other ones back, and this might reduce the number of steps. So the basic premise of the problem remains the same, that no larger disk on top of smaller disk, and all n disk at start begins with peg A in an descending order of size from bottom up. And you have to transfer all disks from peg A to peg B using auxiliary disk set peg C and peg D. So see, now this solution has been proposed by Frame and Stewart. It is also called the Frame and Stewart algorithm. It is proposed in 1941. First, let us try to understand how do we formulate this problem. So one way to think of this situation is that if I cut out a chunk of those n disks and move it somewhere, then the remaining chunk of those disks, without hampering the part where I just put the first part, I could use the 3 pegs and then move it to destination. Or to make it more clear, let's say we have n disk, everything is at peg A. Now I just remove a chunk of those disks. Let's say I remove a chunk of n minus k number of disks from peg A to peg D using peg B and C. And then I just, the k disks that were there remained in peg A, I just try to put it in the destination and then move the rest n minus k disk which was waiting for me again back here. But 4 pegs are here. So let us start thinking it one by one starting from the basic solution. So if n less than 3, what do? I just do it using 3 pegs. Using my solution, 2 cube minus 1 is the maximum number of steps. So 2 to the power n minus 1. So if n is less than 3, I do not even need the 4th disk at all. 4th peg at all. So therefore what I will do, I will just use my earlier thought algorithm with 3 pegs and just try to transfer it. So this is my base case for n less than 3, which is equal to the whatever be the solution that I get for 2 to the power n minus 1. Otherwise, the concept that I was telling, that I will fix a value of k, how and which is better and all that we will try to justify in a minute. I will try to fix a value of k which is in between 1 to n. And I will try to keep the k largest disk on peg A and transfer the smallest n minus k disk from peg A to D. Okay. So while doing it, now when I transferred those top n minus k disks from A to D, I have B, I can use B and C. So this transferring of top n minus k disk is again a recurrence solution of using the same function or formulation that I can use. Now the last k disk I would transfer from peg A to peg B without disturbing the smallest n minus k already placed in D. Therefore, this largest k disk, everyone is larger than whatever I was there, the n minus k disk was there in peg D, so I cannot place anyone there. So I have to resolve this transferring by using 3 peg only. That is, my peg C is my auxiliary here. So again, this number of disks, the movements will be of the 3 peg. It will be the tk thing. Finally, the smallest n minus k disk I could use 4 pegs also, because these are my smallest disks. So anywhere I can place. Peg B now contains k largest disk. So even if I can use peg B to replace some of the disk there and finally put it back on top of whatever is there in peg B. Pictorially, let me reiterate what I am trying to do. I am trying to find a k, so I need to transfer all these disks from peg A to peg B. I am trying to find a k such that I could cut through it, and first this n minus k instance I put it here at peg D. Since I can use any of these 3 pegs, so all the 4 pegs I can use. So this n minus k is a smaller subpart of my recurrence that I solve while putting it here. The number of movements for n minus k will be of the recurrent nature while putting from A to D. Now what I do is that I try to put all these larger disks from A to the final destination. See, while putting it here, I cannot use this peg anymore because all the disks are larger. So any of the disks while moving from A to B, if I try to temporarily keep also in peg D, this is restrictive because this size will be more than whatever is there on top. So this problem of transferring k disk to peg B I will solve using 3 pegs only. Finally, when I try to put back the n minus k number of disks here, I can again use the 4 pegs because all of these disks are smaller. So even if one disk I put up and place here, that is also permissible. Whereas in this case, I could not put any disk here. Any of the disk from A to D. I cannot put it in this configuration. So therefore, when this light blue part of all the disk from peg D, I put it back in peg B, then I can use again the 4 pegs. So first, the light blue part we can use 4 pegs. The dark blue part can use only 3 pegs. Then again the light blue part can use the 4 pegs also. Depending on that, you can see the recurrence is as follows, that if Hn be the Tower of Hanoi problem of moving n disk with 4 pegs, putting n minus k disk with 4 pegs to peg D, putting the k disk with 3 pegs from peg A to destination, that is the Tk is the earlier recurrence that I have developed while transferring n disk with 3 pegs. And Hn minus k is again putting back those n minus k disk temporarily I have put in peg D using all the 4 pegs as I explained back to B. So this is the overall movement of the problem. And what is the base condition? It is, you have seen that if it is less than 3, I will just use the 3 peg problem as my answer. So it is 2 to the power n minus 1 provided n less than equal to 3. So how to solve this? Gradually we are moving to a scenario where the recurrence are getting complicated, and maybe the accurate solution of it, we are not finding suitable way to expand or some mathematical jugglery to solve it. This necessitates that we somehow need certain kind of formalism or certain kind of technique to learn to solve this problem. On the contrary, we can have an approximate version of it. So let's say that though it will depend on the best choice of k, and we will try to see that approximate answer, does the approximate answer give some best value for k or not. So for simplicity, let us assume n equal to u into k. So n is a multiple of k. That's what we assume. So un is 2un. So this is the formula, recurrence formula. So un will be 2 this plus 2 to the power k minus 1. So it is approximately equal to up to 2 to the power k. So minus 1 I just, for larger n, I can just remove by approximating the solution. Again, this is a good form to expand. Let us expand it. And we go. So all of them are approximating because un minus k is again expanded without this one form. That's why I put an approximation in each step. If I took this one, this will be equal to otherwise. So if these all steps are approximating my answer till this point. Now when I reached here, I reached a point where I get 2 to the power u minus 1 uk plus all this. Now this is just nothing but, since my uk is again 2 to the power k minus 1, right? Because this is a base condition I have reached, and this base condition says that it is 2 to the power k minus 1. Again I approximate by eliminating minus 1. So this is again approximation. So all this inside it, you will get, it's a sum of these numbers. So finally you will get, it's a 2 to the power u plus k, which is equal to 2 to the power n by k plus k, because u is n by k. You know, this approximation of the whole result and best choice of k, after a long time it was been devised by Paul Scottmeyer. And you will be amazed to see that this approximation is minimized with this, and un is almost 2 to the power 2 root n, because k equal to root n gives this number as 2 to the power 2 root n. And finally, that this is the optimal number or the best number of movements possible, or this beyond which you cannot do it. This is proved in 2018, that is 2 years back. So see, the recurrent problems are ever posed and it is ever solved with it. So with this set of examples, I tried to give you a journey that starting from a recurrence problem, how you formulate it and how you try to use another recurrence inside it to solve it, how expansion can solve it, how there are methods where you cannot solve it directly, how you can approximate it, and what are the nuisance and complexities involved in it. So with this background, it is now our time to only look for suitable or devise suitable methodology to solve such kind of a recurrence. So our next set of lectures will just concentrate on how we can solve such kind of a recurrence. To start with, let us start with very easy or very good looking type of a recurrence, and we will gradually complicate up to this type of very weird looking or tough kind of a recurrences and try to mathematically solve it. Good looking recurrences. So we give a name, as in the introductory session, introductory class in slide we show you that there are first order, linear, homogeneous, and every name has a purpose. So let's say we start with first order, linear, homogeneous recurrence with constant coefficients. So what is first order? First order means that your dependency of a function is only with respect to the previous instance, that is one instance less. This is the first order. What is linear? The function that you compute is of linear type. So it is not a squared, cube or log function. It is just Tn plus 1 equal to Ctn. So this is not log Tn plus 1. This is not Tn square something. So this is a linear. What is homogeneous? So the recurrence function that you define, Tn plus 1, is dependent on some constant into Tn without any other function to be added which is not Tn. So a different function constant, if it is added with this format, then we call it non-homogeneous. So this is homogeneous. So we just have to direct it from the previous thing without any constant values. What do you mean by constant coefficient? You see that coefficient of Tn plus 1 is 1. The coefficient of Tn is C, which is a constant. So all the coefficients that occur with the recurrent function is of constant type. So this is first order, linear, homogeneous, constant coefficient recurrence. Boundary condition, as we saw, T equal to B. So you know how to solve it because you have already solved it using expansion. So it's very simple because C into Tn equal to C into Tn minus 1, which is again C into Tn minus 2 becomes C square Tn minus 2. So it will go by C to the power I Tn minus y as a general term, and it will finally converge to C to the power n T0. So C to the power n equal to Tn minus n T0. So T0 is my B. So the answer is B into C to the power n. So the mathematical formulation of such kind of a recurrence is directly C to the power n. Some examples: an equal to 3 an minus 1, where n greater than equal to 1, a2 equal to 18. See, just I put some jugglery here that I just directly do not say you just n greater than equal to 0 and do not give you T0. So since you have this recurrence and a2 you are given, so you can directly say a2 equal to 3 into a1 equal to 3 square into a0, so you can get a0. If you get a0 and you have n greater than equal to 1, so you can easily formulate this recurrence with the same formulation and go by this is my answer. An equal to 2 into 3 to the power n, because a0 is 2, which is b, and c is 3. So 2 into 3 to the power n for n greater than equal to 0. And you put n equal to 0, you will get 2. That is a0 equal to 2. You put n equal to 2, you will get 18. So this is your final closed form result from the recurrence using our formula. Practical problem: how many number of different summands of n? If you remember that in many of the counting lectures, we just try to show you the summands as the different summands of 3 become 3, 1 plus 2, 2 plus 1, and this. When we try to compute the summands of 4, one way to compute the summands of 4 would be just to add 1 with the last element, that is 3, 1 plus 3, 2 plus 2, 1 plus 1 plus 2. That is the first row. The second way is to just append plus 1 with everything. 3 plus 1, 1 plus 2 plus 1, 2 plus 1 plus 1, and 4 1 pluses. So here there will be plus 1. This is plus 1 is missing here. So 4 1 pluses. So this is basically the summands of 4. So which means that for every summand of 3, I would have 2 times the number of summands in 4 gives us this recurrence. Sn plus 1 equal to 2 into Sn. With n greater than 1 boundary, and you know the summands of 1 is just 1, it can be expressed in only one way, that is 1. To directly apply the formula, you have to say that I have Sn plus 1 equal to 2 Sn. So let us assume that Tn equal to Sn plus 1, which formulates that Tn equal to 2 Tn minus 1, and then you solve it by T0 equal to 1, and it gives you Tn equal to 1 into 2 to the power n. So we can directly also, looking at this, you can directly also say that Sn equal to 2 to the power n minus 1, because you go till 1 and just expand it, or maybe use this formula. So the only limitation to use this formula is that I have n greater than equal to 0 and T0 equal to b. Here I have n greater than equal to 1 and T1 equal to 1. To make n greater than equal to 0 and get T0, I just shift the function parameters by assuming Tn equal to Sn plus 1, which translates this function into Tn into n equal to 2 Tn minus 1, by making this conditions and the base conditions same. So this gives rise, so now I can directly apply, because everything matches with my general format. So it's 2 to the power n minus 1 is the answer. So the number of different summands of a number is 2 to the power of the number of n minus 1, which is the 2 to the power n minus 1 is actually 2 into the number of, which are the number of summands for n minus 1. So this is some examples, practical examples, when we use first order linear homogeneous recurrence with constant coefficients. Let us try to complicate whatever we started. First order linear homogeneous, instead of constant we have a variable coefficient. Let's say Tn plus 1, your coefficient is variable. So see, there could be variable of n placed here also, but what we could do is we could divide it directly here and make one particular function. So that's why this is a general form. So you could have f1n Tn plus 1 equal to f2n Tn. So then I will make Tn plus 1 equal to f2n by f1n into Tn. So f2n by f1n is itself a function of n, so it's a fn. So that's a generalized form. And your T0 is b, where b is a constant. So how do we do it? Again, if we go by the form of expansion, it will be that it will be fn minus 1 Tn minus 1 for Tn. Now Tn minus 1 will be fn minus 2 into Tn minus 2. This will go on, and when this will go on, you will reach till b0. It will be b. You will reach till T0. It will be b into all the multiplications starting from n minus 1 up to 0. Right? Up to 0, because T0 you have to reach. So it will be T1 equal to f0 T0. So it will be f0 plus f into f1 into f2 up to fn minus 1 into b. So that is the product form. Example, factorials, because factorials of n fn equal to n into factorial of n minus 1. So this, if I consider this as fn, then it will be n into n minus 1 into n minus 2 into so on, where your b is f0 equal to 1, the 0 factorial is 1. So this we get fn equal to n factorial, while n greater than equal to 0. Next example. So here you see that we have first order non-linear with constant. So earlier we started off with everything there, first order linear homogeneous with constant. Now we have first order non-linear homogeneous recurrence with constant coefficients. So we introduce non-linearity. It means that, let's say it is t to the power k, Tn plus 1 to the power k. It's a non-linear function now. Everything else is there. It's first order. It has constant coefficient, but just homogeneous, but it's just non-linear. So to eliminate non-linearity, one of the approaches that we just take this function as Rn, a different function. So Rn equal to Tn to the power k. So the recurrence now becomes Rn plus 1 equal to c into Rn, because this function is straightforward now. However, since Rn equal to Tn to the power k, your base condition becomes R0 equal to T0 to the power k, which is b to the power k. So now if I solve this recurrence, it will be Rn equal to R0 into c to the power n, that is b to the power k into c to the power n. as per our previous slide formula. Now this Rn I have assumed Tn to the power k, so I have to root it k. I have to take the kth root of everything, so the final answer is this. See, what I have done here is that I just took a linear function to replace the nonlinearity or to eliminate the nonlinearity. Instead of this t to the power k, a simple variant let us take as an example where it may be a log function as well, log an plus 1 equal to this. So let us take this as log a, bn as this. So now the whole thing will be bn plus 1. Remember, I wrote a subscript n plus 1. It is basically a function with n plus 1 as its argument. So this will be bn plus 1 equal to 2 into bn with b0 equal to 1 because b0 is log a0 is 2, so log 2 base 2 is 1. So don't forget to transform this also when you go for exchanging the general format of given recurrence into a linear recurrence and form it as a linear recurrence. So then I get bn equal to 2 to the power n into b0 which is 1, so it is 2 to the power n. Now an, see now the an becomes 2 to the power bn because bn I have assumed log an base 2. So the answer is 2 to the power 2 to the power n. So here to solve the nonlinear recurrences, first order homogeneous with constant coefficient, we just need to transform the nonlinearity into a linear form and then try to transform the base as well. Then solve it using our known formula of first order linear homogeneous recurrences and then give it back again to the nonlinear index by transferring it back. The other thing, we talked about linear homogeneous always. Now let us also see the other format of homogeneity which is non-homogeneous. So as we have said that non-homogeneous means that it will be dependent not only with Tn but also as a function. So earlier this Fn was 0. So you have only these two terms. So non-homogeneity means your Fn is not equal to 0. So when this is the case, your Fn is not equal to 0, which means that you have now, so this format and this format are equivalent, only c equal to minus d, I have just transformed it. So now if you try to estimate it using expansion, it will be c Tn equal to, check this form, Tn plus 1 equal to this, which means Tn equal to c Tn minus 1 plus Fn minus 1. C Tn minus 1 is nothing but c square Tn minus 2 into Fn minus 2. So it will be c square Tn minus 2 plus c Fn minus 2 plus this Fn minus 1 as it is. Now if you expand it, you will get this kind of a format. If you expand it in your pen and paper, you will get this kind of a format. Finally, c to the power I, this term, and all this Fn minus 1 into c Fn minus 2 into c square Fn minus 3. You can see that this is c to the power k Fn minus I plus k, this term. So finally this, when you go till the base, that is t0, will be t0 c to the power n, so b c to the power n. This form is finally when you go till n is this one. So now the question is that if you can solve this one, so this closed form formula is very accurate. We will see in this lecture that one of the examples where you can directly solve this summation. But it is not always the case. Your choice of this function may directly lead you to solve the summation very easily. So in the next set of lectures, we will also see that how such functions or how such non-homogeneous functions we solve. So for this example, let us take the simple thing. You have already written codes of binary or bubble sorting, selection sorting, insertion sorting. So what does it do? So if you try to sort the nth element, let's say you are taking selection sort, so or let's say insertion sort you are taking, you have already sorted n minus 1. The nth element you will try to compare with previous n minus 1 positions and try to place it actually in the position it belongs. So the worst case you take is this much. See, here the non-homogeneity comes. So the number of comparisons you make in insertion sort in the worst case comes, and the solution becomes, you apply this formula when your a1 is 0. It is 0 plus k equal to 1 to n minus 1. Your c is 1 and your fk is just n minus 1 is your f, this one. So this will become n square minus n plus 2, which is order of n square. So you can also see for the bubble and selection sorts, this similar recurrence of the number of comparisons you can formulate. But the takeaway here is that this comes as this kind of a formula, and if you can solve this summation into a closed form very easily, then you can just go by this formula for the non-homogeneity. For counting and sequences, we can also see which is the common form of this kind of a sequence. If you try to see here that each difference is just 2 into n. So n difference of 0th element A0 and A1 is 2, that is 2 into 1. The difference of A1 and A2 is 4, that is 2 into 2. The difference of A2 and A3 is 6, that is 3 into 2. A3, A4, 8, A4, A5, 10, A5, A6, 12. So you can see that every element, so A1, this is 2, 4, 6, 8, 10, 12. So you can see that An minus A0, if I try to compute, it is nothing but 2 plus 4 plus this. Because A6 minus A0 is the sum of all of this. Because A5 will cancel out, A4 will cancel out, and so on. So here the recurrence is that the nth term is n minus 1th term plus 2 into n. This term is this term. So an minus 1 is equal to 2n. So a1 minus a0 is equal to 2 into 1. a2 minus a1 is equal to 2 into 2. a3 minus a2 is equal to 2 into 3. a4 minus a3 equal to 2 into 4. So an minus 1 will be equal to 2 into n, where my a0 is 0 as I know. So this is basically a recurrence generated by this polynomial. So this is an example of a non-homogeneous recurrence relations. To sum up with a little bit of twist, we have first order linear non-homogeneous along with variable coefficients, which is a mixture of whatever we learned in today's lecture of solving. That is Tn plus 1 equal to Fn Tn plus Gn. This is non-homogeneity where Gn not equal to 0. And this is variable coefficient where we do not have a fixed C. Similarly, by expansion, if you just expand it as we have done so long, you will get this closed form. I will not go into expanding it in details due to cluttering. You may take a pen and paper and just expand it. This is just the closed form that you will get. So B into this one, because earlier you get B into C to the power n when this was a constant for you. Here you have Fn, so your Fn is variable over n, so you have to just vary n. So this is that part. And this is you got again C to the power k. Your k will now vary with respect to how many sum k value in the sum you have. So here with respect to the sum value this will vary. So this is C to the power k part inside. And Gn minus k, because earlier when you use non-homogeneous function as Fn, you get Fk. Here also due to the indexing, you will get such kind of a function. So intuitively in today's lecture, we have seen that how we define recurrent problems, how we try to solve the recurrent problems using certain observations over it, and what are the kind of recurrences we formulate over that. So we have seen methods where we directly solve it by using the mathematical or algebraic juggleries, and in the later part of today's lecture, we have also seen that there are a technique or a closed form derivation that we could find out, and we have seen very elementary recurrence, which is first order linear homogeneous recurrence with constant coefficient, and we varied the constant with a variable coefficient, homogeneity with non-homogeneity, linear with non-linear, and see the variations with respect to all of these formulations and solutions. In the next lecture, we will also try to complicate the recurrences and see how complex recurrences we can formulate and solve. Thank you.